Hello, my name is Anthony Kennedy. This is my oscillations lab. In this lab, we will study the effect on the trajectory of an object attached to a spring by composite forces. The energies, the spring potential energy, the gravitational potential energy, and the kinetic energy are also very important for this lab. These are my fundamental physical principles, more namely the Newton's second law with its accompanying velocity and position update. This allowed me to predict the future location of the object attached to the spring. As you can see here on the right, you have a picture of the model. You have the fixed point, which the spring is attached to, the object attached to the bottom of the spring, and the man who released the spring from rest and began the oscillations. The force of gravity and the spring force were also very important for the oscillations of the object, and the work energy theorem informed a lot of the coding that I will do further into this presentation. The, my system accompanied the Earth, the mass, and the spring, and I didn't have any surroundings. I did this so that the total work would equal zero, and so I could calculate all components of the delta energy, including the spring potential change, the gravitational potential change, and the kinetic energy change. I also had the same spring constant between the model and the experiment, to create consistency between them. I calculated it based off the period, and I used both, based on the period of the video, and that created like a link between the experiment and the model to reduce error. The start point I used was directly under the fixed point, which you'll see will inform the initial velocity. Yeah, when I started the tracking, I measured my first position right when it was directly under the fixed point. This created an initial velocity, which I had to calculate. However, the calculations were not exactly precise. This definitely was going to cause error in my system. You also have the friction from air resistance that's neglected inside the model, which was represented in the experiment, of course, because it's in the real world. And in the tracker, even though there was quite a few data points I chose, it could not compare to a model which is iterating over thousands of points. So that was definitely going to cause some discrepancies in my data. This is the slide where I compared the models versus the experiment. As you can see, a few things that I mentioned before. In the model, there was many more data points, so it was much more, precise. It doesn't have the friction and drag calculated in, like it's just apparent in the real world. And of course, the imprecise calibration and the imprecise velocity. The delta E, one thing I want to note, is not necessarily zero. When I put it into the model, it oscillated ever so slightly up and down. I was not able to get rid of that. However, that may have affected the velocity updates in relation to the experiment. What does it mean? Is energy conserved? Yes, energy is conserved. The delta E on my graph, right, was effectively flat. I kind of wish I placed it on that slide, but that shows that the actual energy in the system was not changing. So yes, my system conserves energy. Um, when I took to calculating the periods, right, from the x and the y direction, unexpectedly, or at least to me, I found two separate periods. I hypothesized that this what came from the fact that the displacements or velocities might have been different in the y and x directions. However, when I calculated my spring constant, I used specifically the y direction. And maybe that would, if I used a spring constant for both the x and the y, I might get a more equal period. Yes. All right. Thank you very much for listening to my lab. You have a wonderful day.